right, I'm looking at the examples on page 3, and I would like to, in the video, go over A and B. And then what I would really want you to do is to pause the video and spend about 8 or so minutes trying the remaining examples on your own. The other questions at the end. So I will make sure to include them. I just really want you to try them and compare your thinking to my thinking. So these are just getting a little more complicated than the examples on page 2. So for f of x, we've got a fraction overall. We've got some junk at the top that involves the natural log, and then we've got some junk at the bottom that's a polynomial function that can't be equal to 0, we know, because we said no zeros in the denominator. So I'm just going to start at the top. So for the natural log, if the natural log the argument of the natural log is x squared minus 3. And we said that as far as domain restrictions go, the argument of the natural log, so this whole thing, that must be positive, so greater than 0, not greater than or equal to 0, because the natural log of 0 does not exist. So x squared minus 3 must be greater than 0. All right, so as we think about that, um, I don't know how much experience you had last year solving quadratic inequalities, but if in doubt, let's go to the graph. We know what x squared minus 3 looks like. We know that x squared is just our parent function of parabola, and that if I subtract 3, that's just going to have the effect of translating that down 3 units. So this is y equals x squared minus 3. If I want to know everywhere this is greater than 0, what I really want to know is where on this graph is y greater than 0. So I could go through and kind of highlight the part of the graph that I'm looking at where y is greater than 0. My highlighter bled over the line a little, but I'm looking for the part of the graph above the x-axis. So let's see. All right, so I would need to know, like, okay, what x values are these? Well, if I think about it, if it's x squared minus 3, that means that really this must be the negative square root of 3, and this must be the positive square root of 3. Because what I think students are tempted to do here, and there's nothing wrong with it, but I just want to make sure we understand, is in this inequality, we can write this as x squared is greater than 3. But I think what we really want to do is go to this graph, x squared minus 3 is greater than 0. All right, so if I were here, if I was solving it this way, if I were to take the square root of both sides, I would need to recall that like I'm gonna get a plus or minus. So like if I take the square root of this, oops, sorry, if x squared is equal to 3, when I take the square root of 3, the square root of 3 is positive. However, when I'm saying that x squared equals 3, there's two solutions. So I know that x equals negative square root of 3 and x equals the positive square root of 3. The problem is, I think when we just do it algebraically without thinking about the graph, we don't know, are we looking for values of x between these values, or are we looking for values of x between negative infinity and negative root 3 and positive infinity? I think graphing it illuminates that for us. So looking at this, I can see that I could use any value of x between negative infinity and the negative square root of 3, because as I go out here left on the number line, I'm getting out to negative infinity. And then I could start at the positive square root of 3, and I could go out to positive infinity. So I could see if I continued my number line, that'll go out to positive infinity. All right, so that's just the domain restriction for the numerator. So that's all we need for the natural log of x squared minus 3. Now we've got to look at the denominator, and the function in the denominator itself does not have a domain restriction. It's just x squared minus 3x. But the fact that it is a denominator, we said that that x squared minus 3x, that cannot equal 0. And because it's a quadratic, we need to consider there's probably two values that would make that equal 0. So here's what I would do. I would set that equal to 0 and solve and find for which values of x that is 0. All right, because this is what we don't want. We don't want that to equal 0. All right, so what we want to do here, first of all, is we want to factor. We do not want to divide by x. If you divide both sides by x, you'll eliminate a solution. So let's factor out our greatest common factor, which is x. So I'm left with x minus 3 equals 0. And using the zero product property that you learned in Algebra 1, when something is in factored form, you set each factor equal to 0 to solve. So the first factor is x. X equals 0. The second factor is x minus 3, and we need to consider if it equals 0. So if I add 3 to both sides, I realize that for the value of x equals 3, that will be 0. Over here for the value of 0 equals x, that's what would make that factor equal 0 as well. So what that means is that if x is 0 or if x is 3, then my entire denominator over here is 0 and the function cannot exist there. So even though we solved with this equal, what we're really thinking of here is that these cannot equal 0 or 3. All right, so we're going to put together our two domain restrictions, or rather from our two parts. We have this information, and that came from the argument of the logarithm. And then we got these two pieces of information from the fact that our denominator cannot be 0. So just like before, I'm going to draw a number line. And on the number line, I'm just going to put these important like boundaries. So I know like negative square root of 3 could go out here. I'm going to have a 0, the positive square root of 3, and then the number 3. And we don't need to space those evenly or anything. We just need to put them in the correct order. All right, so we said that this first domain restriction that we could go from negative infinity to the negative square root of 3. So I'm just going to shade that. But you know what? I'm going to go ahead and put that open circle there because x cannot be the negative square root of 3. All right, in fact, let's go through and put the rest of our circles. X cannot equal 0, x cannot equal the positive square root of 3, and x cannot equal 3. All right, so we've got these two checked off, and we've got this part checked off, so we've just got to look at this last piece. X can be between the positive square root of 3 and infinity. So that would be from here, except again, we said it can't be 3, and then keep going. So it turns out this middle piece, like it doesn't really matter that we find out x cannot be 0 because it was never going to be 0 based on the numerator. So our final answer here for this example, the domain of f of x, I know I'm kind of writing into the next example space. Sorry, the spiral is never big enough. The domain of f of x is going to be from negative infinity to the negative root of 3, or from the positive root of 3 to 3, but we've got to stop there because it can't equal 3, or, and I'm going to scooch kind of off the page here, sorry, from 3 to infinity. So when we read this, we can see where these interruptions are. There's a big chunk of the number line right here where that function does not exist. And when we see that 3 is the boundary in two places here, that just tells us that x cannot equal 3. All right, so that's the domain for A, for f of x. All right, let's look at one more of these together, and then I'm going to ask you to try the remaining 3. All right, in part B, on top, and in fact, I'm just going to kind of do this so I don't get confused. All right, in part B, on top, we've got the tangent of t over 2. And if you recall the domain restriction for tangent, if we scroll back up, we said that for the tangent functions, that the domain restriction is pi over 2 plus pi times n. And so if you're like, what are we going to do with that? It's not actually as bad as you would think. We've just got to kind of get there. All right, so for the tangent, the argument of the tangent, so the t over 2, that cannot equal pi over 2 plus pi times some number n, where n is an integer. So we need to understand the domain restriction. We need to know what t cannot be, not what t divided by 2 cannot be. So what we could do is we could multiply both sides of this, I'm going to say equality, even though it really cannot be equal to. We're going to multiply both sides of this by 2, just like you could an equality, or an equation rather. Man, words are hard for me sometimes, especially when I'm doing calculus videos on a Saturday. All right, so these are going to cancel out, and we'll have t cannot equal, and then we've got to distribute this too. So t cannot equal pi over 2 times 2 is just pi, plus pi times n times 2 is just 2 pi n. So t cannot equal pi plus 2 pi n. That's the first restriction, and we get that from the tangent function. So if you think about it, this is really just a way to generate a bunch of other values t cannot be. So like if n is 0, t can't be pi. If n is 1, t can't be 3 pi. If n is 2, t can't be 5 pi. So I'm not gonna, like, we can't obviously put every one of those values on a number line. Let's just see what happens with the rest of the domain restrictions, and then we can go back and reassess. All right, so 4 minus t squared in itself is a polynomial function, but we've got the square root function and the fact that that's in the bottom of a fraction, the denominator, so we've got to consider that. So we need to consider two things. Let's just do the square root part first. The parent function, the square root of x, we said that for that to be true, x must be greater than or equal to 0. So for the square root of 4 minus t squared, 4 minus t squared must be greater than or equal to 0. So just like I did before, I want to graph this. 4 minus t squared, or negative t squared plus 4, is going to have a y-intercept of 4. And since the quadratic term is negative, I know it's concave down. You could also factor this like a difference of squares and say like 2 minus t times 2 plus t has to be greater than or equal to 0. That's going to help us think about these numbers. These numbers have to be negative 2 and positive 2. And we could plug those back in. But you could also just get that from factoring. And if you just set these equal to 0, we'll get negative and positive 2. All right, so what we want is for this function, we want to know where it's positive. So if I look at the graph, I know that it's positive everywhere that the graph is above the x-axis. So the domain restriction that I get from that part is that that function can exist between negative 2 and positive 2. So I'm going to put a big rectangle around that. And that already is kind of telling me that that first domain restriction with the tangent function might not actually be that important. It's always fun when you do a lot of math and then realize that like it didn't matter. When you get to the next part of the problem, that happens quite a bit in calculus, if I'm being real honest with you. And we just don't want to get frustrated. It's just something that that happens, but we want to consider it every time. All right, so the last part of this, I'm going to look at the overall fraction. I'm going to think of that as just 1 over x. So if I just think of like tangent of t over 2, just let that be, like, I'm not even going to worry about that. I'm going to replace that with a 1, but I'm going to think of my denominator as x. And I know that when I have a function like this, x cannot equal 0. So what that really tells me over here, because let me actually back up. I think I had that in mind when I did this last piece. If we go back to what we got over here, these should actually be brackets, because based on this being greater than or equal to 0. All right, but I hope we can agree that when I plug in a negative 2 to this function 4 minus t squared, or a positive 2, that's what makes it go to 0. So since we now know that the square root of 4 minus t squared cannot equal 0, because that is our x, that's our denominator of this function, I now know that t cannot equal negative 2 or 2. So it just changes this domain restriction to be parentheses, negative 2 to 2.